Well, it's a thrill to be here. I notice on Members Online, a lot of people I know. I was surprised to see them. And I understand that I'm supposed to spend 20 minutes talking about how I got involved in astrobiology before I take questions. So I will try to do that. I'll try to make it 20 minutes long. So I have an extensive background in science. I started out in physics. And I didn't like labs. One of my big problems, I didn't like labs. So I took the senior level, all the senior level courses in physics, solid state physics, quantum mechanics, general relativity, etc. But those were the courses you didn't have to have labs. And I also had 2 years of chemistry, including organic. And I had, in addition to that, extensive background in geology. I was almost a geology major. And a year of biology. So I had an extensive background in science, couldn't decide what to major in. Discovered philosophy my senior year, loved it, and it ended up that it was easiest for me to graduate with a degree in mathematics because I had to have all those math courses in order to get the science background. So I ended up being an accidental math major. And it was really quite fun. I graduated with a BA in math, and basically, went on with my BA in math, and spent 2 years as a computer scientist, software engineer. And I also ended up going to philosophy. I didn't have a philosophy degree, but with my math degree, I was able to get into Brown University to study philosophy, and I got my PhD in philosophy. But of course, I've always had a strong interest in science since I have an extensive background in science. Accidental math? Oh, that's great. That's great. I think there are a lot of us. Actually, in philosophy, there are quite a few of us. I've been surprised at how many philosophers say to me, oh, yeah, that's what happened to me, too. So I was it turned out at Brown, I had expected to be able to do logic and philosophy of science, but they lost their logicians and philosophers of science. And so I ended up doing metaphysics, which is not, for those of you who are philosophers know, that's not like what they do in the metaphysical bookstore. It's asking really foundational questions about causation, space, and time. And you do draw on science. I think good metaphysicians do. They think a lot about what science tells us about it, and they also think about more general issues. But anyhow, I ended up at... I did a postdoc at Stanford, where I was basically a postdoc in philosophy and computer science at the Center for Studies in Language and Information, and came to the University of Colorado Boulder, which is a center in space science. It has more NASA grants, I'm told, than any other university in the country. And that's when, in the mid-1990s, I switched careers from doing metaphysics to doing philosophy of science. And it happened with the Allen Hills meteorite. Many of you probably know about the Allen Hills meteorite. The Allen Hills meteorite was discovered. It's basically a meteorite that was discovered in Antarctica. And they know it's from Mars. There are a number of them that have been discovered in Antarctica because it's a good place to look for meteorites. If you find something on the ice is very thick, it probably came from above, rather than having been something from below. So they go and collect meteorites there. But anyhow, this meteorite was collected long before its significance, or the controversy that surrounds its significance, occurred. And what happened was that it sat around for a while, and then somebody cracked it open to look at it. They knew it was from Mars because the isotopic ratios of the gases in the interstices of the rock were not consistent with the Earth's atmosphere, but they were consistent with the Viking lander results for the Martian atmosphere. And they discovered these really interesting structures that looked a lot like fossilized microbes that you find in areas in Australia that date back 3.5, 3.6 billion years in terms of their structure and their chemical constitution. And so this news was released to the public in advance of the publication, which I believe came out in Science, and immediately there was a storm of controversy. Time magazine had this wonderful headline called "The War of the Words," play on the War of the World, and Boulder decided they wanted to get on board, because it is a big center of space science, and decided to have a panel discussion on the Allen Hills Meteorite, and they wanted a philosopher of science. And since I was teaching philosophy of science, although not actively doing philosophy of science, I was trained in philosophy of science at Brown, they came and asked me would I be part of the panel. And I sat down and thought about the controversy over the Allen Hills Meteorite, and I realized there were a lot of confusions about what you'd expect looking at an historical event, because the meteorite, if these were fossilized Martian microbes, they were long dead microbes. This was looking at specific structures in a rock and trying to infer what those structures represented. So when the panel discussion occurred, I was the only philosopher, and I gave my talk, and as I walked back to the panel, who were all scientists, a couple of them grabbed my arm and said, "We learned something." And I was rather astonished. I didn't know whether to be offended or flattered, because it was odd that they thought that they might not have learned something. But at any rate, I was invited the next year by Bruce Stokowski to join a team, a proposal to the brand new Astrobiology Institute. And the Astrobiology Institute had just been formed. It had been formed partly as a result of the discovery of the Allen Hills meteorite, because there was great interest in the possibility of Martian life at that stage. And he invited me, as I said, Bruce Stokowski wanted us to Boulder to have a representation on this. So he invited me to join them, and I spent the first two cans of the Astrobiology Institute. I was a funded member of the Astrobiology Institute. I'm still affiliated, but I'm not funded right now. But anyhow, that's how I got involved in astrobiology, and it's been really fun, and it's been a center of my work in philosophy of science. I ask bigger questions, but I almost always draw on my research in astrobiology, issues about particular historical science, origin studies, origin of life, origin of water on Mars, etc. And that's really how I got involved in astrobiology, and it's been absolutely a great pleasure. So I think I didn't spend quite 20 minutes, but you can ask me further questions about that if you wish. But I'm happy to take questions from the audience and from some of my friends that I see up there in the members online. So the question is, as a philosopher, what are your biggest frustrations with modern science education? That's a great question, and my biggest frustration is the naive way in which scientific methodology is taught. When I teach my Introduction to Philosophy of Science, which is actually directed at non-science majors and often the science students who are in it, it turns out it does satisfy a science requirement, so I get a lot of science students, non-science students in it, who really hate science, and they're astonished to discover that science actually is very creative and exploratory. They were raised basically in elementary school, middle school, and high school with this view of the scientific method that goes back to Francis Bacon, which involves the idea that scientists are these consummate logicians. It doesn't stress the inductive reasoning except insofar as it claims that it can be done like a computer. So they have this idea that they have to look at all this information and then they have to, by some kind of magical, logical process of induction, basically infer a hypothesis and test it. So it's very cookbook-like. And they don't understand the remarkable ingenuity that goes into coming up with a creative hypothesis, and that there are multiple hypotheses one can come up with. Some are better and worse than others. Some of them are very exciting and original. It takes great ingenuity to do that, and it takes great ingenuity to design an experiment to test it. Yeah, I would agree with Kelly. That's certainly true. For every complex problem, there is a simple, easy to understand, incorrect answer. That's definitely the way in which, and students end up not liking science because they see it as being not at all exciting or creative. But I have had students, okay, let's see. Could you tell us the story of how you came up with the term shadow biosphere? That's a really fun story, actually. I had gone to the Centro de Astrobiología in Spain in 2003, and I wanted to learn some biochemistry. And I knew they had. I also thought it would be fun to spend a semester, a year actually. It was supposed to be a year in Spain. It would be an exotic thing to do. But I also wanted to learn some biochemistry, and they had a lot of microbiologists and biochemists there. And so I spent some time talking to them. I was out in the field at the Rio Tinto, which is a Mars analog. It's very acidic water, and one time nobody thought there was any life in it, and then they discovered it was just full of microbes. It was quite surprising. They just hadn't gone and looked. And when they went and looked, they were like, well, it's not too acidic for life, because look at all these microbes. So I was talking to them about, well, if you had a sample of soil, how would you identify the microbes in it? And they proceeded to tell me about, there's microscopy, there's cultivation, and then there are, in those days, it was primarily PCR, which required primers. This was before the days of the mass metagenomic methods. And as they were talking to me about this, I said, you're not going to recognize a form of life that's microbial life that's very different from our form of life. And they immediately said, oh no, that's not true. And then they thought about it, and I challenged them. I said, how are you going to recognize it? So we had this long debate, and the final result of this debate was they conceded they probably wouldn't be able to recognize it. And then they formed a big meeting to discuss this further, and I went to that meeting, and that's where the term shadow biosphere came up. I was debating, I said, should we call this dark biology? And I said, no, shadow biosphere was the right term. As I thought about it, and we kind of debated it, because such life, even if we couldn't detect it with our current microbial techniques, such life would be at least shadows, traces in the environment, because it would use material and excrete material and its metabolic processes. So we should be able to see traces in the environment of it if we were looking for them, but the kinds of methodology that was currently used by microbiologists wouldn't detect it. And that's how the term shadow biosphere was invented. Yeah, no, it's the great news that it stuck. So this is from Kelly. How do you envision the process by which we will eventually formulate a general theory of life? In particular, what role will provisional definitions, or whatever you want to call them, play? I'm very opposed to provisional definitions because they involve supplying necessary and sufficient conditions. I think the problem with necessary and sufficient conditions is that they completely box our concept of life. And the difficulty is that something either fits those conditions or it doesn't. And I think we're likely to overlook particularly life that's very different from ours if we go with the definition. What I prefer is to, I think the best way to formulate a general theory of life is to look for alternative life descended from a separate biogenesis. That was the inspiration behind the shadow biosphere, or life, extraterrestrial life. But I think that if it's very different from ours, we'll miss it if we use a definitional approach. That's why I support what I call tentative criteria. In my forthcoming book, which I'm on the last chapter of, it should be out soon with Cambridge, is called The Quest for a Universal Theory of Life, Searching for Life as We Don't Know It. I argue that we should be using tentative criteria rather than definitions. And tentative criteria, the basic idea here is that you have a group of criteria that are associated with Earth life, but you also look at features that might not be associated with Earth life. And if you find basically a system a system that's provocative in the sense that it has features that are Earth-like, what we'd expect with Earth life, and features that differ, and it has enough of those features, then you subject it to further investigation. Because the problem is we're dealing with a single and potentially unrepresentative, and I argue in the book we have reason to think it may be unrepresentative at the biochemical level of life. So that's my answer to Kelly. And I'll just continue, I guess, down the list, and we can go back to these answers since it seems like I have another list. from Richard Gordon, what's your opinion on the I can't pronounce it, Meteorite study BBC just ran? The Meteorite and the hidden hoax. I don't know anything about that study, but I definitely will be looking it up. Let me write it down afterwards. I haven't seen that, and that sounds very interesting, and I would really like to know more about it. But alas, that's something I haven't caught yet. So, sorry about that. So from Shanna Kendall, what are some of the bigger questions that should be kept in mind as NASA proves looking for life on other solar system bodies? I think the biggest question that should be pursued as you look for life elsewhere in the solar system is that it might be quite different from our form of life, and we don't know what the biochemical possibilities are. So we know, for example, that our form of life, that even modestly different forms of life would not fit. So for example, our form of life uses the same 20 amino acids out of over 100 possibilities. And it uses amino acids of L-chirality when you could have amino acids of D-chirality. You can't get mixed chiral mixtures, but you can, there's no reason to think that our form of life couldn't have been D-chiral in terms of the biochemistry. Same with nucleic acids. Nucleotide bases, we know that there are over 12 possibilities compared to the 4 or 5 since we have a switch between RNA and DNA, thymine and uracil, but we know that there are other possibilities, modest possibilities. We don't know how different they could be. Now Titan, I think, is a more interesting place to look, to be honest, than Mars, but that's kind of my take on that. So the next question is, which directions you envision for the origin of life field? What do you envision for the next 50 years? So that's a very interesting question about origin of life field. I think that, I hope that we're getting away from, sort of bare RNA worlds, this dichotomy between metabolism first and basically gene-based reproduction first. I think it's going to be much more productive if we look for hybrid models of the origin of life, because it just seems very naive to think that we had RNA molecules replicating and getting to be better replicators and longer, and suddenly one of them said, gee, I better code for an amino acid. It seems more likely to me that they grew up together. These molecules are extraordinarily complex, and the more complex you get nucleic acid to be, the harder it seems to me it's going to be for them to code for proteins. So I suspect that a hybrid model is the best way to go, and I think there's some evidence that's where people are going. So Richard Gordon is summarizing the meteorite story. Recurrent dreams of life in meteorites in Genesis in the beginning. Oh, he summarizes that. Yeah, so I'll follow that up. Any other questions or follow-ups? Let's see. Laura has a question above Richard. Oh, okay. What tentative guidelines, definitions for life do you propose in your forthcoming book? I argue against definitions. I think we should not be interested in... So the reason we shouldn't be obsessed by defining life is because definitions supply necessary and sufficient conditions. That means that everything that satisfies the definition is alive, and anything that doesn't satisfy it is not alive. If you get a form of life that differs much at all from our form of life, it's going to be classified as non-living. The only thing a definition is going to do is allow you to recognize life that's very similar to our form of life. It's going to be useless, I think, for going to Titan and for looking at life that descended from an alternative origin and maybe has a very different chemistry. So that's my big concern with that. Let me just check and make sure I've answered. So I propose using tentative criteria to search for alternative forms of life. And the basic idea here would be that you might look at something such as systems, physical systems that are out of equilibrium, because I think all of life, wherever it's found, is going to be an out of equilibrium system. You might look for certain kinds of complexity, but you aren't going to use these as necessary and sufficient conditions for life, but rather as criteria for making you suspicious. You might even look at features of our form of life that aren't general to all life, but are unique to certain environments. So if you're looking at a very dry, deserty conditions like in Mars, you might look at the kinds of how life is different in the Atacama Desert and how it is than it is in the rainforest. I'm thinking of microbial life. So once you have, if you get enough of these criteria, and you find a system that seems to satisfy some of them, but on other ones it doesn't seem to qualify as living because it's quite different from our form of life, then that system is worthy of further scientific investigations. And that's basically what I'm proposing in my book. Let's see. So Richard Gordon, has anyone deliberately created proteins of mixed chirality? Yeah, they don't. My understanding is mixed chiral protein. Protein chemists tell me they've certainly created non-standard proteins out of abiotic, out of amino acids that are not among the 20 that have been used by familiar life. You have to. There are certain constraints. You have to have the right. You have to have the right sequences of hydrophobic and hydrophilic, large and small, etc. Molecules, amino acids, but you can create non-standard proteins. The problem with mixed chirality is that the proteins don't fold correctly, they don't maintain their structure well. So really the only way you can get good non-standard protein structure is with homochiral mixtures. But you can get them with chiral amino acids. You can make perfectly good proteins that would be functional in the right organismal environments. Let's see, I think there's another one down here. Oh, good. To clarify, this is Laura Grace Beckerman. To clarify, you said that you were proposing using tentative criteria. What are those tentative criteria? You just suggest that we should use them. I think that, I think some of them would be being a system that's out of equilibrium, that basically shouldn't be there. A local system on another world that shows evidence of being out of equilibrium, and it's not easy to explain it in terms of non-biological processes. Looking for certain kinds of complexity. These are the kinds, but I'm not I'm not the best person to pick the kinds of criteria that you're going to have. These are just some of the ones I think should be included, and I think that you could, and the idea here is you're not going to, if it's really strange life, it won't satisfy all of them. But if you get enough of those, and then there are others it doesn't satisfy, which if you're using a definition would condemn it to being not alive. That's what would happen with the definition. If you took these criteria as defining criteria, then you would dismiss it as being alive. And my suggestion is that we don't want to do that. We want to look at such systems and investigate them further. And this is what I think is going to be the foundation for a general theory of life. Because you cannot generalize from a single example that you have good evidence for, may be unrepresentative. So Kelly Smith, why should a definition necessarily involve something so specific as particular? Oh, it doesn't. But the problem is, and if you want to avoid the D word, we can call what we use whatever you think like. I think first of all, a definition doesn't, of course, have to be as specific as particular chemical bases. But the problem is if you get too abstract, you lose the features of life that are distinctive of life. So, for example, if you were interested in water and you looked at its very abstract functional properties, such as the fact it's a good solvent, you would classify chemical compounds, such as nitric acid, as water. And in fact, at one time, we had agua fortis and agua regia. It's not an accident they were called water. They were considered strong waters. So, so let me continue. Let's see, with Kelly, I'm losing him here. So, so I think that the problem is that we just don't know at what grain a good definition of life would be. And it's also important to realize that scientific theories, successful scientific theories, don't give you necessary and sufficient conditions. So, for example, people say water is H2O. And what H2O does there is tie into modern chemistry the salient feature, but a single molecule of water doesn't have temperature and pressure. And when you get enough molecules of water together, they actually break into ions, and so it's not pure H2O anymore, and they form secondary structures, dimers and primers, which are primarily responsible for the distinctive features of water, such as the fact that it expands when frozen, which is very unusual, and remains a liquid over a wide range of temperatures. And as philosophers, I think we want to not call something a definition unless it is a definition. Words matter, concepts matter, and most of the scientists who do talk about definitions do have in mind necessary and sufficient conditions. So I think it's important, if you really want people not to become confused, to call it something other than a definition. Let's see. So I guess here's another one. What would be the first thing you would like to know if, when we encounter with alien microbial life? Well, I really am going to want to know if it's on Mars, how much like our life it is, because there is some reason to wonder whether we might be Martians. We know that 3.8, 3.9 billion years ago, and now they've pushed life on Earth back to 4.1 billion years ago on the basis of carbon isotope ratios. The Earth was not a particularly good cradle of life. It was being slammed by the late heavy bombardment. There's some controversy about whether that actually occurred now, but I think in general it's thought that it did. The late heavy bombardment, it's thought, would have plastered the crust with gigantic meteorite impacts, melted, certainly vaporized the oceans and melted the crust. And so the issue is that Mars may have been a much better cradle of life at the time at which life first arose, which is looking like it's 4.1, 4.2, 4.3 billion years ago. At least the latest isotope ratio evidence suggests that. And so I think that the really interesting question, if we find microbial life on Mars, is how much like ours it is. So I think that's a really interesting question about Mars, because when Mars was slammed by heavy meteorites, we know that microbes can survive, bacteria can survive being transported in a meteorite to Earth. There have been studies that have indicated that. And of course, meteorites that are slammed off Mars are going to fall inward toward the sun. We know, we have meteorites we've actually found, as you know, in Antarctica. So I think I'd be really curious about, whether it was much like Earth, and then how different it was. And then I would begin thinking, we have the beginning, shall we say, empirical evidence to start considering generalizing. So, Richard Gordon, regarding mixed proteins, would they be any worse than distorted proteins, which contemporary Earth life utilizes? The problem is that the core proteins used by contemporary Earth life are the patterns in which they fold are critical to their functionality. If they don't fold in that way, and there are diseases that result from that, then organisms die. So it's really important that proteins not only have the right sequence of amino acids, but that they fold in the right ways so that they expose catalytic surfaces in the right way. And so, it's generally agreed that heterochiral amino acids just wouldn't form functional proteins of the sort that are needed. Let's see. This is from Sanjoy. One of my favorite papers in grad school was yours on historical versus experimental science. Can you tell us more about it and how you developed those ideas? Yeah, so that was the first, that actually related right to that came right out of Allen Hill's meteorite. So I was going to talk about it, but I wasn't sure we had enough time. So the Allen Hill's meteorite, the debate that was going on when I actually looked at it, really kind of floored me, because people were talking about why they weren't trying to falsify the claim that it had fossilized Martian life. And it occurred to me that when you talk about falsification, you're talking about generalizations. You falsify, claim all A's are B's by finding something that's an A but not a B. And so the big question was, how to explain what was going on here. And yet they were talking about falsificationism, and I was deeply puzzled by that. And then I began thinking about historical research and how it works, and I realized it doesn't work in that way. And so I studied, I particularly paid attention to the end Cretaceous extinction because it's one of the great success stories of historical science. And I discovered that, it was a very different process that you saw in so basically there's something called the KT boundary, which separates the end of the Cretaceous, the age of the dinosaurs basically, and the beginning of the Tertiary, which is now called the Paleogene. It's been relabeled, and that's where the beginning of the modern era animals, mammals and plants that we know today. And what I noticed was that it was evidence in that particular boundary, which wasn't very big. It ranged from about an inch to a couple inches, depending on how close it was to ground zero for the meteorite impact. And there was all kinds of evidence in there. And so they generated multiple hypotheses originally, particularly when they discovered iridium anomaly in there. Iridium is a heavy element, like other heavy elements. It sinks to the center of the Earth during planetary formation. You've heard the Earth said to be have a core of iron. Well, other heavy elements also, basically migrate during the time the Earth was molten to the center, so that the crust is depleted in the heavier elements. And so it was really interesting because people were saying, well, maybe it's volcanism. So what you do in historical science is you proliferate multiple hypotheses, and then you look for what I call a smoking gun to discriminate among them. And one of the things that discriminated between the volcanism hypothesis for the end Cretaceous extinctions and the meteorite impact was the discovery of a certain kind of shock quartz, which is cross-hatched. And you only find it in two different places. They looked at supervolcanoes, and they didn't find it in the kind of quantities. It's in massive quantities in the KPG boundary sediments. And what they discovered is that you only find it in two places, the sites of nuclear explosions and meteor craters. And the same with the iridium anomaly. It turned out that supervolcanoes aren't associated with the iridium anomaly. So there's a number of different things that they discovered which went together to form a smoking gun that suggested that of all the hypotheses that had been entertained, the meteorite impact hypothesis was by far better supported. And this was positive evidence. They were not able, on the basis of evidence, and they didn't try to falsify, for example, the hypothesis, which had been around, that it might have been due to a pandemic. It could have been, it was. There was a pandemic just before the meteorite impact or just after. But the probability of that compared to the massive increase in what we know a massive meteorite impact could do, particularly one about the size of Mount Everest, which is how big this thing is estimated to have been, was a much more plausible hypothesis. So that's kind of the story. I'm happy to expand on it, about how I came up with the work in historical science versus experimental science. So it's quite different, the work in historical science, but equally grounded in empirical evidence. So, hi Carlos, good to see you too. Aside from what life is, what other philosophical issues do you see in astrobiology? What do you see as the central topics in philosophy of astrobiology? Well, I think there are a lot of interesting topics in the historical sciences. So, one of the big questions is, how wet Mars was. As some of you probably know, people thought that a lot of the water on planets comes from comets, and there's new evidence just a couple of months ago that can't be the case because cometary water has the wrong isotope ratios, and so now people who thought that cometary water was the source of water on Earth and on Mars are back to the drawing board, arguing that it may come from minerals in the crust, chemical reactions with minerals. So there's just lots and lots of interesting questions that are not biological about how do you explore the solar system. You're not going to be able to run experiments very readily. You're going to be doing modeling. So one of my big interests is in going forward after the book is done is looking at the role of computer models, particularly modeling in historical science, but also modeling in geology in general. The focus, of course, has been on climate, but there's a lot of modeling that goes on in the geosciences, which has been ignored, and that's an area that I want to turn to. And my focus will be, I will be relating it to the geosciences in general, but I'll also be using, as I've done consistently in my work, lots of examples from planetary science. So I try to use both kinds of examples. So let's see, where am I here? So I think Chris Miles, what are your thoughts on synthetic life research? Or do you see this research valuable to astrobiologists? That's a wonderful question because I'm writing on that in my book right now. I've just finished it. So I think that the problem with synthetic life research, such as Vintner's minimal cell, which recently has been on the news, is that it's so closely based on our form of life. So what Vintner has done is basically taken a genome and built it by scratch and managed to figure out what genes can be removed and have the genome survive inside a cell. So he's taken, he's tried to come up with a minimal genome. Some of the genes that he needed to do this, he doesn't even know what they do. But the basic idea is to have a minimal genome. And then he took out of another cell its genome, but he left everything else about the cell intact. He just inserted this minimal genome into the cell that had its genome removed. So we really don't have a different form of life here, a novel form of life. And it's very hard for those people who are trying to work with that, who are coming up with alternative amino acids or are using all expanded genetic, alphabets for DNA. The problem is a lot of the non-standard nucleic acid bases that have been used in some of that work, they're not going to be transcribed and they're not going to be replicated by DNA and transcribed by the genetic machinery of the cell. So the result is that only a few, and you have to pick them very carefully, will actually be replicated in a cell if you create an artificial genome of some of them. And so I don't think you're going to find with synthetic life research anything that's very novel. That's the worry I have. I think that you're going to see variations in our form of life, but you're not going to find anything, I don't think, that's very novel. I think we really need to find, and that's my emphasis on the shadow biosphere, we really need to find extraterrestrial life or a shadow biosphere if we want to find a truly novel form of life. So, Sanjoy, what are your thoughts on terraforming Mars before we're certain whether or not it hosts life? Well, I'll be honest, I find terraforming Mars really rather amusing, given that we can't seem to even maintain the Earth, let alone terraform it. I think we'd be much better off terraforming the Earth as it's getting destroyed than thinking about terraforming Mars. I think by the time we're actually capable of terraforming Mars, we'll be pretty sure whether or not it hosts life. I think that's far distant, and I think nobody quite knows how to do it. And the problem is we know so little about, quite frankly, affecting global environments and global climates that we're liable to wreck it as much as terraform it. And given our current, shall we say, success, I would say wrecking it is more likely. So, Chris Miles, to follow up on my last question, what are your thoughts on computer models in artificial life and artificial chemistry? Again, the same worry about artificial life as I expressed earlier. So if you're talking about hard, soft day life, the idea that Thomas Ray is one of the people who claimed that he had created life in a computer simulation. He had basically, in Tierra, that's the name of the simulation, the basic idea is that he had the computer programs of Tierra compete for CPU space, and so he claimed that they were engaging in the same kind of Darwinian evolution by natural selection that our form of life does. But of course, he's tacitly presupposing that life is just the ability to perform Darwinian evolution. And that's really the question at issue. And similarly with people who have autopoietic theories of life, they're doing the same kind of thing. They're assuming that abstract metabolic processes are what constitutes a living thing. If you look at, for example, the properties of water, you could simulate them, but simulating the properties of water, is not going to get you real water. And I think that if we look at the history of life, history of scientific research, it's really easy to simulate something by just logical relations among immaterial parts in a computer. It's much harder to get the molecules to do it. It's much harder to get actual causal relationships among material parts to do those things. A paper, for example, bridge will not support my car. A simulation of a bottle of water blowing up in a simulated refrigerator is different than an actual bottle of water blowing up in an actual refrigerator. So I think that you're presupposing that life is just an abstract functional kind, and I think that's the very question at issue. Is life like water, or is life like a song, which can be instantiated in many different things? I think that's the issue, and we don't have an answer to that. And I would suspect it's more like water than a song, particularly given the complexity of the biomolecules of life as we know it. So let's see where I am now. Let's see. So this is from Kelly again. But suppose we have the technology to terraform Mars, and we know it contains only microbial life. Should we leave Mars to the Martians, as Carl Sagan and Chris McKay argue? I probably would. I probably wouldn't think that would be the case. I mean, the issue, it seems to me, is that if we discover microbial life in Mars and we have a good understanding of that microbial life, I think we can protect it to a certain extent. Yes, you'll change Mars, but the environment's always changing. In less than 1 billion years, the sun will expand out and sterilize all the terrestrial planets anyhow. So I do not feel as strongly about this issue. It's not. I think there's a difference between microbial life and intelligent life. So let's see, Sanjoy, the angle of my question was more towards the ethics of transforming. So with regard to the ethics of transforming Mars, I don't see a problem with transforming Mars. If you could do it, I have great doubts about whether you can terraform Mars to make it habitable by people in anything like the near future. And I think the future of humanity is not very, given climate change right now, is not very, shall we say, positive. And I think if we could terraform Mars, we could clean up our own climate. And I think that would be a far better thing to do. But if we could terraform Mars, and we've already scientifically looked and know what's there, then I think doing it carefully would be okay. Yes, I don't think that would be an ethical problem. Any more questions? Any words of wisdom for early clear astrobiologists when it comes to including philosophical thoughts in their science? Philosophy is everywhere. I mean, you can't really if you do science by ignoring philosophy, then I'm going to say something very strong. You're not doing good science. There are fundamental questions that are philosophical in every scientific disciplines. And philosophers are the people who are trained to think critically about these issues and to contribute to scientific discussions. So I think it's critical I think that, the possibilities that you're able to consider as an astrobiologist are going to be much wider if you are trained, you have some training in philosophy. I know when students take my introductory to philosophy courses, their responses are often, wow, I never thought about this, or this is really interesting. And some of them go on to get PhDs, and they come back to me and they say, I really owe you for the way in which I now think about this particular problem. So, Carlos, I'm worried that there is tension between the argument that proteins must be homochiral and the argument that we cannot know anything about life because we only have a single example of it. If you're right about homochirality, isn't that something we know about life everywhere? About our kind of life, yes. About about proteins that are made of amino acids, I think that's correct. But again, the question is whether or not you could have proteins like ours. The question is, when I talk about homochirality, I'm talking about the origin of life on Earth. I think that when you have proteins like ours, it's definitely the case. They have to be homochiral. But I think if you're talking about life that originated in very different environments, let's take Titan, where there's no liquid water available, and it's a very different kind of environment. I don't think we know. I really don't think we know. Let's see, Kelly Smith. I know this will surprise you, Carol, but I actually agree with you on the need for better appreciation of philosophy and science. No, it doesn't surprise me, Kelly. I have to run to deal with a home inspection, but thanks for, oh yeah, thanks. Good talking to you, Kelly, and I'm not surprised you agree with me. I think most philosophers would agree with me on this. I'd be surprised if they didn't. Good luck with your inspection. What do you do for fun? Well, among other, I hike. I like hiking a lot, but I also dance the Argentine tango. So, that's something I've done for years. I'm in Pittsburgh as a visitor. Oh, really? Yay. Hey, maybe if we run into each other sometime, we'll have to dance it together. So I know people are really astonished. I used to dance it much more seriously than I'm doing now. I haven't danced it for a year because I've been basically at the University of Pittsburgh as a visiting fellow in their Center for Philosophy of Science. But when I go back, and I'm leaving on Saturday to go back, I'll be back to dancing it. Tango Saikon, well, that's interesting. Philosophers dance it too. A lot of mathematicians and engineers. It's surprising. It's a really sort of highbrow dance. I've been surprised by that. So, let's see. So here's another question by Laura Beckerman. Are there any philosophical questions from science fiction or any other fun media that you love thinking about on the side? Yeah, I mean, I do enjoy science fiction. So I do, so how about a few remarks on being a woman in philosophy? Oh, so let me, so I'm not sure how to answer that. I often entertain possibilities for for truly alien forms of life, and it's always fun reading science fiction. So I guess this is something that I've really thought about, and I owe it to science fiction, concepts like the Borg and other hive intelligences. I really wondered about hive intelligence and how sophisticated it could be, technologically and otherwise, because ants are quite sophisticated, and there's new evidence for bees. Some people are debating. I just saw recently, I haven't read the article, that there's an argument that bee brains are such that they may be conscious. Now, I wouldn't go that far, but there's some things, and I haven't read it, but I thought that was intriguing. And I was also intrigued about the possibility of distributed intelligences. So yes, I really thought about, I think that the hive intelligence stuff has been really very motivating for me to think about, but it would not be something I'd write about. Unless I were writing science fiction, but it's certainly something I think about. And here is the question, Batul, I'm not sure how to pronounce your name, which is why I've been avoiding it. How about a few remarks on being a woman in philosophy? Challenges and advantages. Well, it sounds like you all know I'm from Boulder, but which department has had some difficulties that have been made very high profile lately. Well, the disadvantages are there are very few women in philosophy. It turns out there was a study, I can't remember if it was Nature or Science, about how the distribution of women across different disciplines, and philosophy was one of the rarer, one of the disciplines with the fewest number of women. It was comparable to physics, although there was some people, I think physics may actually have more women, but it was like economics, engineering, I think physics still had fewer women, but I'm not sure about that. But it's on the extreme end of fields that don't have women. And I think, and it is challenging because I think women in general have a more of an uphill road. That is to say, when a woman gives a talk, she's automatically thought to probably not be as good as a man. That's my experience. And she has to prove herself in a way that a man has already given the benefit of the doubt. So I don't see a lot of advantages. But I managed to survive it. And I have my own horror stories about it, and I have my own successes. And I think it's probably getting better for women in philosophy. I think that there are some really great places for women to do philosophy. Here at Pittsburgh, where I am at the university, at the Center for Philosophy of Science, I had a great time. It's been wonderful. Laura is back as a major Trekkie. I appreciate your thoughts on the board. Yeah, I'm a Trekkie too. So, Laura, do you think tentative criteria should also be applied to determining sentience or consciousness? I don't know the answer to that because I find consciousness even more difficult in life, and I think life is really difficult. So I think probably tentative criteria, but it's easier because it's easier to recognize intelligence, I think. And I think if you find intelligence and it's natural, it's probably should be considered to be sentient. As far as robots, they're built to primarily to function, to behave like humans, artificial intelligence. I think that's highly problematic. And interestingly enough, artificial intelligence, despite the hype, has not been as successful as it originally thought it would be. And I think that's very interesting and perhaps telling. I started out doing programming, artificial intelligence programming, back in the dark ages when I had just graduated from college with my degree in math. And people had the view that we were, by now, it would be like 2001. That is to say, you have artificial intelligences that are conscious. We're still very far away from that, and I don't think we're really getting closer. We're getting able to make better and better expert systems, but one of the unique aspects of human intelligence is its generality, not its expertness. So I'm skeptical about artificial intelligence. But I think that if you ran into natural intelligence, it would probably be pretty easy to tell that it was intelligent. And if it's intelligent, I think you could discuss with it whether or not it was conscious. But you'd have to have a philosophical discussion about what consciousness and sentience is. It would be a lot of fun. I would enjoy that. Good science fiction book. Somebody ought to write a story about this. Well, if not, upstairs. Okay, well, if not, get my book. It'll be out soon. You're welcome. Everybody's welcome. It's Cambridge University Press. The Quest for Universal Life, Searching for Life as We Don't Know It. And I see that somebody just put my book up. Thank you, Batul. I'm going to sign off now. Thanks, everyone, for your questions.